Today I'll be talking to you about a string matching algorithm using finite state automator. Whenever you use a search engine or a find function like sed or grep, you are utilizing a string matching program. Many of these programs create finite automator in order to efficiently search for your string. The idea is to first build a finite automator for a pattern, like the one shown here, which will then pass your given text through to see if the pattern occurs. The actual matching time of the algorithm is big theta of n, but the pre-processing, i.e. generating the finite automator, can be much larger, and I'll come to that at the end. If you don't already know, a finite automator is a 5-tuple, as shown here, where Q is a finite set of states, Q0, which exists in Q, is the start state, A, which is contained within Q, is a set of accepting states, sigma is the finite alphabet, and finally, delta is the transition function, which takes an input and a current state and produces a new state. Okay, now for the example. Assume we've already generated this finite automator using the pattern P, and we want to search the text T to see if this pattern exists. Okay, first what we do, we start at state 0, and we pass the text T into it until we've matched all 7 letters of the pattern and end up at the accepting state 7. Okay, starting with the beginning of the text, we're in state 0, and we pass an A into it, and we transition to state 1. Now after processing an A, we then process a B, and since we're state 1, we traverse to state 2. But then what happens if we process a C? For this automator, it is not shown in the diagram, but if the transition of a letter is not shown, then assume a transition to state 0. Here we have another C, but as it's not the required A, we still remain in state 0. The same again is also true for the next letter B, we still remain in state 0. Now we come to the stage in the text where we finally read in an A, and then transition to state 1, and now we have a prefix of 1 matched again. Now after receiving B, we have a prefix of length 2, and now back to state 2. Now at state 2, if we receive an A, then we move to state 3, and if we receive anything else, we lose everything and are back to state 0. Now at state 3, if we read in an A, then we move back to state 1, and if we read in a B, given here, we continue forward to state 4. At state 4, we read an A, which allows us to transition to state 5. Now currently at state 5, we receive a C, which moves us to state 6. But what happens if we receive an A? Then we will move all the way back to state 1. And if we receive a B, then we still retain a prefix of AB, AB, and we only return to state 4. So now at state 6, we receive an A, which takes us finally to state 7, which is the accepting state, and we have successfully matched the pattern. So this is the idea. We first need to construct this finite state machine for the given pattern, and now we'll see an algorithm for doing just that. This algorithm generate transition function is the pre-processing part which generates the transition table which is used to create the finite automator. For the example we looked at earlier, here is the transition table. Now onto the algorithm. First, we compute the length of the pattern. Then we are trying to fill up the table for all the states and all the characters that are possible in the alphabet. So we loop through the number of states or the length of the pattern. Then we loop here through all the characters and we calculate the minimum value between state q plus 1 and the final state. Then this repeat loop ensures we've found the maximum prefix length, and then finally assigns state Q to the transition table. So now, what will be the complexity of this pre-processing algorithm? Well, for this loop, we'll run n plus 1 times. This loop will run sigma times. And this section here will run m times. So the overall complexity will be big theta of m squared mod sigma. Now we have generated the transition table, all we do now is pass it into this matching function and loop through the text until the final state is met. The complexity of this matching algorithm is simply big O of n. Thank you for listening. I hope you now have a better understanding of string matching with Finite Automator.